Quantum computing has a marketing problem disguised as a physics problem. The pitch is simple. A sufficiently powerful quantum computer will break RSA encryption, the mathematical lock that secures virtually every online transaction. Governments are spending billions preparing for that day. The assumption, rarely questioned, is that classical computers cannot compete. We decided to test that assumption, not theoretically, empirically. Over 5 weeks, we built a quantum circuit simulator in Rust on an Apple MacBook and ran Shor's factoring algorithm against increasingly large numbers. No quantum hardware, no cloud. Just a laptop and a question. Where exactly do the walls appear? RSA encryption relies on the difficulty of factoring large numbers into their prime components. Shor's algorithm, published in 1994, exploits quantum superposition to find hidden periodicity in modular arithmetic, turning an exponentially hard problem into a tractable one. But implementing it classically means simulating every quantum state. The standard circuit needs 3n plus 1 qubits to factor an n-bit number. Each qubit doubles the state vector. A 25-qubit simulation requires 512 megabytes. 40 qubits would need 16 terabytes. The exponential wall arrives fast, but the standard circuit is wasteful. Iterative phase estimation, described by Mosca and Ekert in 1996, reuses a single qubit in place of an entire counting register. The qubit count drops from 3n plus 1 down to n plus 2. For n equals 143, that means 10 qubits and 16 kilobytes, instead of 25 qubits and 512 megabytes. We implemented both. The standard circuit took 273 seconds. IPE factored it in under a millisecond. With IPE, the memory wall receded far enough that a different wall came into view. Shor's algorithm is probabilistic. Roughly half of all attempts end in what textbooks call dead ends. But Clark Alexander, a mathematician at Argentum AI, noticed that the dead ends were not dead at all. Standard polynomial factorizations, the kind taught in second-year algebra, could extract factors from every case the textbooks said to discard. The impact was immediate. N equals 522,719, the product of 727 and 7019, factored in 21 qubits using just 32 megabytes. Standard Shors would have needed 58 qubits and 4 exabytes.
These algebraic factorizations are not new mathematics. When the period ER is odd, the expression a to the r minus 1 factors as a minus 1 times the geometric sum. A pair of GCD computations, taking microseconds, often yields a factor that the standard algorithm would have thrown away. Similarly, when a to the r over 2 equals negative 1 mod n, the expression a to the r over 2 plus 1 factors into 2 terms. Same trick, same microsecond cost. These identities are absent from virtually every implementation of Shor's algorithm we have found, from textbooks to IBM's Qiskit tutorials to published research code.
Each factoring attempt is independent. Fresh random base, fresh quantum register, no shared state. A classic embarrassingly parallel workload. We ran attempts simultaneously across all 8 CPU cores. For moderate problems, parallel attempts gave a 5-fold speedup. But for larger problems, we discovered something fundamental. Gate-level parallelism and attempt-level parallelism share the same thread pool. On 8 cores, 8 simultaneous attempts each get effectively 1 core. The 2 levels of parallelism cancel out. This is not a bug. It is a constraint of classical computing. A quantum computer faces no such trade-off. The parallelism is in the superposition itself.
The quantum Fourier transform applies rotation gates of angle pi over 2 to the k, where k increases with the number of qubits. At k equals 177, this angle, approximately 5 times 10 to the negative 53 radians, becomes smaller than the minimum distinguishable rotation allowed by Heisenberg's uncertainty principle. No physical qubit, no matter how well engineered, can execute a rotation that the universe cannot distinguish from zero. Since Shor's algorithm requires 2 registers, the maximum useful circuit is roughly 354 qubits. There exists a number somewhere around 100 decimal digits, above which no quantum computer can factor using Shor's algorithm. Not because of engineering, because of physics.
The conventional narrative is not wrong, but it is blurry in places that matter. Classical simulation goes much further than most people assume. By mapping exactly where it fails, we establish the lower bound of quantum advantage. Everything below that bound is marketing. Everything above it is physics. Meanwhile, 2 engineers on a MacBook factored a 6-digit number using an algorithm that was supposed to require a quantum computer. The algorithm worked. The quantum computer was optional. The wall, when we finally hit it, was not in our code. It was in the uncertainty principle.
That's one more step on the journey. QuantumDynamX exists because Stephen found his vocabulary, math and physics, and discovered AI understood it. Yours might be completely different. Music, medicine, storytelling, law, whatever you know deeply. Subscribe if you want to find it. Like if this session clicked. And drop a comment, tell us what vocabulary you bring. See you in the next one.